Welcome back. Thank you for returning. Anything that we should discuss before we get started today? All right. Just a reminder, I haven't added new problems yet, but I will after the lecture. The problems are over here. There's also this anonymous form in case you have any comments about how the course is going. Especially if things are slow, too fast, too complicated, too easy, whatever. If you could let me know, that would be great. Also, feel free to let me know in person. That's also great, of course. There is a tutorial session today as well in the same place. Today I guess, starts at 4. Like the slot starts at 4, and I will be there at 5. Okay. Great. So as we discussed yesterday, we were talking about definitions and constructions. Today I wanted to talk about existence problems. So there's a reasonable question about what that even means. So I wanted to start off by saying that it doesn't mean the following. So here's something that we already know, which is the most basic sort of existence question you might ask. So here's a theorem. Suppose you have, let's say, closed-oriented four-manifold. Then every homology class, integral homology class, second homology class for M is represented by a closed surface. So for every x, there exists some sigma 2, inside of M, a submanifold such that this surface, this submanifold, if you consider the class its class, it will be that x that you started off with. So this is the most basic sort of existence question you might ask. I just wanted to point out, I mean, we are low-dimensional topologists, so we're used to having this sort of thing occur, but this is like a non-trivial thing in full generality. So in general, if you're looking at high-dimensional manifolds, it's not the case that every k-dimensional homology class will be represented by a k-dimensional submanifold. In fact, it's even an interesting question whether there's even a map from a manifold representing a given homology class. This is something called the Steenrod problem. Tom worked on this. That was like his first really cool, awesome stuff that he did. There exist, for example, 7-dimensional homology classes in 10 manifolds that are not even represented by maps of manifolds. So, there is a slogan that like, oh, 4 manifolds are hard and nothing really works there, but many things really do work there, and this is an example of something that works out very nicely in dimension 4. There's a nice short argument here. Again, as I mentioned, this is really meant for people who don't work on surfaces in 4 manifolds, so experts, sorry if you've seen this before, but okay, is that a question? Question or just hand? Okay, great. All right, so let's just look at this proof. It's nice and short. I'm just going to sketch this, not talk about, yeah? If you like, you can have it be smoothly embedded. You'll see in the proof if you like. I didn't ask for M to be a smooth manifold, so I can't call it a smooth submanifold necessarily. But if M is smooth, it will be smoothly embedded. Other questions? All right, so let's do the proof. Again, I'm just going to sketch this and leave you to work out the details. So you have X in H2 here's the one case where orientability will come in for us. I'll use Poincare duality and see that the Poincare dual of X is a class in H upper 2. Now we need a fact from algebraic topology. We have H upper 2 of a manifold. So whenever you have all classes in H upper 2 of a space, these correspond to homotopy classes of maps into the Eilenberg-MacLane space with that group in that index. So by that I mean, in this case, these correspond to maps from M to KZ2. This is an algebraic topology fact. And then second algebraic topology fact is that KZ2 is actually CP infinity. Now we use the fact that M is a 4-manifold, and therefore its homotopy equivalent to a 4-dimensional CW complex. So these maps into CP infinity, you can really think about them as maps into CP2. Okay? So we can use cellular approximation to get a map, let's say F sub X, going from M into CP2. And now this is where the categories will come in if you're keeping track. So here's going to be a non-trivial statement. So we're going to perturb so that we can assume that Fx is transverse to the CP1 sitting inside of CP2. This is a fact that in smooth topology, maybe you're very comfortable doing. The fact that you can do this in topological topology is much more complicated, but it is still true. So maybe this is a fact from differential topology that we're using. And then we define, once you've made this map transverse to CP1, we define sigma to be the pullback of the CP1. Now finally, this is the part that I'll leave for you. You have to check that the class of the sigma is in fact equal to the X that you started off with. That completes the proof. Okay. So perhaps you're most comfortable doing this in the smooth setting, in which case just insert that statement over there. It is a fact that in the smooth setting, you can perturb maps so that they become transverse to your preferred submanifold of the target space. And what does it mean to be transverse? It means in particular that when you pull that thing back that you're transverse to, you get a submanifold. That is the statement of transversality, of a certain flavor of transversality that I will let you look up on your own time. Okay? Yes, sorry. That's a great. That's a great question. This is definitely something that's worth thinking about. So observation about 4-manifolds. So smooth 4-manifolds are homeomorphic to 4-dimensional CW complexes. All manifolds are homotopy equivalent to CW complexes. It is not known whether topological 4-manifolds are homeomorphic to CW complexes, which is pretty weird. That seems like a pretty basic question that we should know the answer to, but we don't. So if all of that is confusing, you should just think about smooth 4-manifolds and move on with your day. I think it's a great question to what extent the proof sort of falls apart in the topological setting. You're right that all of these facts that I used kind of only use the fact that you're homotopy equivalent to a CW complex. You do have to trace through those facts to sort of make sure that you actually do get a surface in the end. I promise you do, but I'm not going to do that on here. But one thing that I can tell you, just as a note for whenever you're worried about things like this, you could always use the following really helpful theorem of Quinn, which says that every connected non-compact Four manifold is smoothable. And what that means is if you start off with a closed Four manifold, you can always remove a point from somewhere. The complement of that point will be smooth, and then you can use your smooth whatever theorems in that complement. And in particular, because this h lower 2 is isomorphic, h lower 2 of the closed thing is isomorphic to h lower 2 of the punctured thing, you can just sort of work through that there. So once you know this very non-trivial, highly useful result, you can avoid thinking about more complicated proofs. That was a longer answer than I should have given. For most of you, it's completely reasonable to just pretend we're always working in a smooth Four manifold. Life is easier that way. Other questions? All right, great. Okay, so this is sort of basic fact. There's a similar basic fact, which I will not prove, and I'll leave it for all of you to prove in the homeworks. Every knot in S3 is the boundary of some, let's say, smooth embedded surface So if the goal is to find embeddings, you always have some embedding. That's the point I'm trying to make, is that the most basic existence question is kind of very easily answered. So the actual existence questions that we ask have to do with some sort of minimality. Okay? So this is saying that, like, okay, fine, you give me a homology class, I can always find some surface, but there's no control over what kind of surface I got. And so the real question that we like to ask is, well, what is the minimum genus of a surface representing a given homology class? Or similarly, for a knot, you know that there's always some surface. What is the minimum genus of a surface that a knot bounds in before? In particular, you'll notice that, like, I still have to convince you later today that not every knot is the boundary of a disk, smoothly embedded disk inside of B4. But there's always some surface. So the obstruction should come from the genus of surfaces rather than just some existence of some surface. That makes sense? Okay, so this was meant to be motivation for the thing that I'm about to write down next, which is like the actual existence questions that we do think about. And you'll notice that I'm talking about both the sort of absolute case and the relative case, just simultaneously. I decided that that was good, but it might also be confusing. So you should tell me if it is confusing. But they are kind of parallel to each other, so I didn't want to preference one over the other. But if it is confusing, you should tell me. But my plan is to sort of keep doing both. All right, so I wanted to tell you, okay, so what are the precise questions that we think about? In the absolute setting, this is called the minimal genus problem. And so that will be given X in H2 of M4, where M4 is some closed Four manifold. The next sentence will be, what is X? I'm going to move the boards first. representing means that the class of sigma is equal to the original class, right? This is usually organized into something called the genus function. So more general, so how to organize this, we have the genus function. Let me notate that as G sub M. This is going to be a map which has domain this H2. And the definition is obvious, right? So you're going to take every class and you map it to right, so right now I'm just giving you some definitions. In the relative setting, you can do the same thing. So you could say define the, wanted to say, there are two sort of very obvious things you could look at here. I asked for these embedded surface. This is what Jean-Baptiste was getting at before. I can either ask for sigma to be smoothly embedded or locally flatly embedded. And then I'll get either the smooth genus function or the topological genus function. Okay? Sorry, I totally forgot about that for a second. Does that make sense? Just, it's not necessarily the same as we discussed. Similarly, we can define the smooth or topological slice genus of knots and it's going to be exactly the same. So this is usually called G4, and then above I'm writing smooth or top. It's a bit confusing. I mean, sometimes I'll write smooth SM and sometimes I'll write top. I just didn't want to write the same sentence twice. And then by definition, this is going to be the minimum of G sigma, such that we have S1 going into S3. That's my original knot K. And as before, we'll have these boundaries. This is just in B4. Sorry, sigma. And then there's that surface in B4 bounding my original knot K. And this will be either smooth or locally flat. And then finally, you'll notice, I mean, here in the relative setting, I decided to write down B4, but there is no reason for me to do that. So we could also consider this for more general Four manifolds. So this is something that some of you saw in the problems yesterday. So we can say, given a closed Four manifold, consider calling M circle to be the complement of some B4. So that means just inside of your smooth Four manifold, you find some smoothly embedded B4, or topological Four manifold, topologically embedded B4, and remove the interior. You notice I've created this extra boundary component called, which is S3. So any arbitrary knot K I can find inside of that S3, and I could ask for the minimum genus of surfaces bounded by that knot inside of this M circle. Okay? So we can define the M genus of K So let's call this smooth or topological, as always. So G sub M smooth / top of K. It's going to be identical to this, really. So that's going to be the minimum genus sigma. Once again, this is my log K, but now this S3 is the new boundary that I've created in M. And I'm asking whether there's some smooth or topological embedding of a surface sitting inside of this M circle. Okay? It's a bunch of definitions. Question? Do you mean in the absolute case or the? Not always. In fact, I'm going to give you some results. So the plan was that I'm going to state some results in roughly the first half, and then in the second half try to do as many proofs as I can. So I'm going to state some results, and hopefully that will answer your question. But not every homology class is represented by an embedded sphere. Yeah? That's a great question. You could definitely do that. So you could say, here I just said M, but you could specify a homology class in M as well. And then instead of GM, you could have GM, comma, that homology class. It's possible, but I think this people have studied and that people haven't. But there's no reason not to. You could. But I did not write that, but I could have, as you say. It's not a satisfactory answer, but it's entirely possible. Here I fixed, right, so I was talking about minimality questions, and you saw that here I fixed a homology class and I asked about minimality. Here I fixed the boundary and I asked about minimality. So I could try to do both. It's completely reasonable. I won't do it. Other questions? All right, let me state some results. Okay. Right, that's what I'm going to do. First, let me talk about the genus function. So first, let me mention this, I don't know, spectacular result of Kronheimer and Ravka to start off. This is from 94. They computed the genus function for CP2. Fully, completely computed the genus function. Here's what it is. So the smooth CP2 genus function is the following. Well, the first thing you have to know or recall is that this is the integers. You remember that, I hope. It's generated by the CP1 that sits inside of CP2. And what they showed is that if you take the integer d inside of here, the minimum genus is this number. And the first construction that I want to show you in the sort of second half is how to realize such surfaces. But realization just gives you like a bound, right? So in order to know that that's the actual number, what do I mean by this? I'm saying that soon I will show you how to construct this genus surface in this homology class. And that will show that the value of the genus function is less than or equal to that number. The really, really hard thing that Kronheimer and Ravka did is they showed that that is in fact minimal. You can't have a lower genus one. This uses Seiberg-Witten something, something, something. Okay. All right. But now to answer your question, let me give you what we know about the topological genus function. This is another spectacular result, this time of Lee and Woshinsky. This is from 97. They showed something about the topological genus function. They showed that this, for D, is less than or equal to D squared over 4. It's the floor function minus 1. And that this is an equality for D even.
For D equal to 1, I guess.
Almost certainly. For D equal to 1, you should get 0. So Paolo, that's an excellent point. You should not consider that formula for D equal to 0. D equal to 1. Is that okay? Okay. But the formula works for infinitely many cases of D, and I'll still hold on to that. Okay. This answers your question over in the corner, I hope. So in particular, for large values of even D, this number is not 0. And so in particular, you don't always get spheres representing, even topologically embedded spheres, representing arbitrary homology classes. It's worth noting that for D strictly bigger than 4, that number is strictly less than this number. So this is another example where the topological thing and the smooth thing are different, in fact, quite different. And it's also, it is worth pointing out that we don't know the rest. The rest is open. So the topological genus function for CP2, I don't know it fully, even though it is fully known in the smooth setting. Question? Yeah? Ah, okay. I see. I see, I misunderstood your question. So the thing that you're referring to of, so it's not necessarily locally flat, but it has potentially some cone singularities, let's say. So that is something that people have considered. You might call that a PL, not quite locally flat. There's some terminology that goes into that. I don't know the answer to the absolute question off the top of my head. I think I would guess that the answer is even then it's not possible, but I'm not completely sure. Certainly in a simply connected setting, every element in H2 is an element in pi2, so you always get a map of a sphere. And I would guess that in more general settings it's not possible, but I'm not completely certain. But let me point you towards, I don't know, let me write it over here. There is something called almost concordance of knots. And that's something in an arbitrary three-manifold you consider two knots to be almost concordant if they're related by a concordance, so an annulus, which is allowed to have PL singularities, PL cone singularities. And there it was shown that, not all knots are almost slice. And so in the relative setting, this might be something interesting to you. But I'm not going to talk about this right now, but that's why I feel like even in the absolute setting, the answer is probably no. Yeah. Thank you. That's very helpful. So also CF results about spinelessness of four manifolds. I guess this was initially considered by Rolfson. More recently, Daniele Ciloria worked on this, and people like Friedel, Nagel, Orson, Powell, etc. If you search for this, you'll find it. Spinelessness, also an old topic. Recent results by Levine and Libman, and maybe Hayden and Picarillo, etc. But I'll stop talking about that now. Questions about these things, though? Yes? This whole thing? Sure. That what you wanted? Excellent. Great. What else you got? Yes. Mark, do you know? Do you know, in the case of D equal to 3, do you know the topological thing? I think that there's like Curvaire-Milnor bounds that tell you that it can't be represented by a sphere. I believe. Yeah, so I mean, if you wanted to look into the Leon-Wilczynski paper, then you would have to do that. But there are also these bounds for specifically about representing classes by spheres, for example, from Curvaire and Milnor, that apply, well, which I think that that would imply that in the D equal to 3 case, you don't get a sphere. But let me fact check that for you later. This is like a very famous result, and I assume that many smooth people have at least seen this and like know about it, even if they don't necessarily know the proof. It's an extremely cool result, and Leon-Wilczynski in particular did a lot of work understanding this minimal genus question in the topological setting. In general, there aren't maybe so many people working on topological questions, at least historically. Hopefully that is changing in recent times. So this is not as well known as it could be. But therefore, I wanted to highlight this to you. This is a really cool, amazing result. But I also want to point out, like, we don't even know the topological CP2 genus function, which is like the simplest thing that you could possibly think of. So there's all sorts of topological things that we don't know. But don't want you to get the idea that we don't know things topologically at all. Oh. All right. Oh, no. No, just. Perfect. Okay, great. So I don't want you to get the idea that we don't know anything in the topological setting. It turns out we do know some things. So in particular, we know the following. So we know that G top CP2 in the relative setting, let's say for knots, is always less than or equal to 1. In contrast to that, the smooth CP2 genus of knots can be arbitrarily large. Okay. I'm almost done with the survey part, but I wanted to point out that sometimes you can have extremely broad general results in, sorry? Which, what? Oh, okay. I heard which middle, and I was very confused. Allison N. Miller, if that helps. There are lots of Millers. This? No, just. Other questions? There's Marco. All right. And then what did I want to say? I wanted to say that more generally, if you have M closed, simply connected, then in fact, Gm of k is less than or equal to 1 for all M, not equal to S4, not equal to S4. So to give you another example of, sorry, top. To give you another example of how in the topological setting, sometimes you can have really powerful bounds that addresses every single thing sort of all at once in a very uniform way. On the other hand, the smooth CP2 genus of knots, CP2 connected some CP2 genus of knots, is pretty much unknown. We have some bounds, but it's like we just don't know very much. But that is a simply connected whatever Four manifold. So in particular, the topological genus is still bounded in the same way. In fact, here we know something more. CP2 connected some CP2, topologically, this thing is just constantly 0. It's an interesting open question. Is every knot smoothly sliced in the K3 surface? It is topologically, in fact, I didn't write that, but it is topologically sliced. There's some partial results in this direction, but we don't really know. And then finally, I forgot to mention something about the absolute setting. I should have said that at the very beginning. My apologies. So back in the absolute setting, G smooth of S2 cross S2 and G of CP2 connected some CP2 bar. These were computed by Danny Ruberman. But those are the only genus functions that we know. We also know the S4 genus function. But that's that's it.
Can they be arbitrarily large, these things?
Yes, that's right. Which one? For
Computed.
computed. Oh, yes. So this is an example of how I made things confusing. This is the absolute setting. So he has an answer for every homology class. But there are no knots in this. My apologies. So then in the absolute setting. It's my bad. It would be very interesting to think about specific knots in these settings as well. Unfortunately, it turns out that they're all sliced. So that is also something in your problems to show that every knot is smoothly sliced in these two four manifolds. So in that case, he did show it for every knot. But I mean, it is known for every knot. Okay. Questions about any of this? All right, so four things go into these kinds of results. There are constructions, and there are obstructions. No one's surprised. So you have to construct surfaces in the given homology class or with the given boundary, whatever. And you have to obstruct, like you have to show that the ones you came up with are in fact optimal, that there aren't better ones. In both cases, there are two sorts of techniques. By the way, this can sometimes lead to some confusions. When I say topological, I really mean locally flat. And as you say, sometimes there is something to be said about more general topological embeddings, but these are the words we use, even if they are not perfect. And when I say this, you should notice that a smooth construction is, of course, locally flat. So smooth constructions are better than topological constructions in a certain sense. So these will give you these, but sometimes you have topological constructions that are purely topological. And that's what I meant here. And similarly, you can have obstructions. There are smooth obstructions and topological obstructions. If you obstruct a topological embedding, you're also obstructing a smooth embedding, naturally. So in that sense, a topological obstruction is, in a certain sense, better. But then there's some things that are really obstructing purely smooth things. That's the distinction I'm making here. So I want to, okay, so what will we actually do? Smooth obstructions are, for example, things that come from gauge theory, Heegard-Floor, Ivanov, etc. I will not tell you about them. I cannot tell you about them. Powell will tell you about them. Next week, other folks will tell you about them. For now, just be aware that they exist and learn about them from the other courses. I'm not really going to talk about them much more than what I've already done. We'll talk about some smooth constructions. I'll do that next. Then we'll take a short 5-minute break. So we can all sort of stretch our legs and whatever, get a drink of water, go to the bathroom. After the break, we'll talk about some topological obstructions. And then if there's time, I'll talk about some topological constructions. Purely topological constructions will be the hardest thing that I talk about today. And because basically anything that's straightforward in some sense will be smooth. So to make something that's purely topological is kind of hard. And I'll say as much about it as I can within the given amount of time after the break. But first, I want to tell you a smooth construction, just to sort of get us up and running. So, oh, right, let me notate these. So I'll do this first, this second, and this third if time. Go till 12, is that right? Okay, thank you. All right, so smooth construction. I just thought it would be fun to see how to construct these surfaces representing that genus. Okay. So here's an example of my smooth construction. All right, so I'm going to construct a surface in this class D inside of H2 of CP2. So you have to remember some facts about CP2. So recall that H2 of CP2 is generated by CP1. But what is CP1? CP1 is an S2. Okay, right? It's familiar, hopefully. So it's an S2 sitting inside of your CP2. It has one more additional property. Its normal bundle has Euler number 1. So it's a smoothly embedded CP1, smoothly embedded two-sphere Euler number 1 normal bundle. Okay, so what does that mean? This means that if I consider that core CP1 and I try to push it off of itself just a little bit, I'm not going to be able to make that push-off disjoint from my original CP1. I'm going to get one transverse intersection. Okay. Almost there. All right, so this means, so let's consider D equal to 2 first. So this will be represented by 2 times CP1. And so I could consider CP1 plus like a slightly pushed off copy of that CP1. Okay? So I could think of this as my original CP1 plus union CP1 just slightly pushed off. That's what that plus is supposed to mean. What will that look like? That will look like, well, here's my original CP1. And because of this Euler number 1 fact, the other copy is going to kind of look like this. I stopped doing the math BB because it's annoying. But fill those in if you like. That point of intersection, if I zoom in, there's a little B4 neighborhood around that point. And what you have to believe is that if I look at B4 intersect the CP1 union CP1 plus, what does that look like? Well, that looks like inside of B4, or inside of R4, I have the XY plane and the ZW plane. They intersect transversely at the origin. And that's a model for what's happening at that intersection. This is kind of tautological. When I say the word transverse intersection, that's what I mean. So you have to decide which one came first. But the meaning of the word transverse is that that looks like diffeomorphic to R4, R4, B4, whatever. Maybe I should stick to B4 and intersect XY union ZW planes. And in particular, this means that the boundary of B4 intersect these things. This is the Hopf-link. That is not obvious unless you've thought about this before. That's another problem that we can talk about in the tutorial. But take this as a black box for now. And so this is extremely useful for me. So let me remind you what the Hopf-link is. The Hopf-link looks like this. The Hopf-links I'll get will actually have signs, but let's not worry about that too much. For either choice of sign, the two components of the Hopf-link bound an annulus inside of S3. So for one choice, you can see that here's the annulus. Okay. And so here's my smooth construction. I'm going to take my representative, which is these two CP1s with that transverse intersection. I'm going to remove the stuff that's occurring in this B4, throw it out, and glue in that annulus that's in that boundary S3. Okay? So my representative, so this is called resolving the singularity. So I'm going to take CP1 union CP1 plus. I'm going to remove two disks and then glue in one tube, meaning that tube, that annulus between these two components. Okay? That is a sphere. That is the number I get if I put in d equal to 2 in that formula. It's homologous to the thing I started off with because the only modification I did was sitting inside of some B4, so that doesn't change any homology information. B4 doesn't have any homology. In other words, these two disks are homologous to that annulus. You might complain that that's not very smooth, because it looks like it has some sort of corner thing. And there's a common thing that every smooth person says at some point. You can smooth the corners. Does that construction make sense? So in that transverse intersection, do this local modification. The intersection is now gone, and you get a surface with this extra tube attached. Yep. Over here. Here. So the resolution is the following procedure. I had these two surfaces intersecting at a transverse double point. So that means that there are two disks. So that means that there are two disks. So abstractly speaking, I had two S2s. And there were two disks, like this and this. In the domain, I had this, let's say. And when I mapped it over to CP2, these two disks were being, they were mapped to CP2 in such a way that these two disks intersected at a single point in their centers. Okay? So you might say that this disk, D1, and this disk, D2, are these disks that are showing up here. So this is the image of D1, and this one is the image of D2. Does that make sense? So it's like, right, I have, on each of these spheres, I have an embedding, but when I consider them together, there's that point of intersection. And the resolution says, remove these two disks. So now I don't have them anymore. So now this is S2 minus D1, S2 minus D2. If I remove these two disks, I leave some boundary on that sphere. And what I've asserted, without proof, is that the boundary is precisely And that's something that you can work out very explicitly, and we can do that together later today. So the boundary is some Hopf link sitting inside of some S3, S3 being that boundary of that B4 ball. And so I have some boundary. I need to fill it in somehow. And I'll fill it in with this Seifert surface for the Hopf link, which is given by this annulus co-bounded by the two components of the Hopf link. And so over in the domain, what that means is I've added a little tube. And I've decided that this tube is going to be mapped over to CP2 as the Seifert surface for the Hopf link. I could have used any other thing inside that B4 that I wanted. I could have picked a surface of genus 20 million. Why would I do that? I'm trying to do something minimal, but the procedure would have still worked. If your goal is to remove the singularity, use any surface you want. If your goal is to minimize the genus, use the best surface you can see. And the annulus for me is the lowest genus. That's why I like it. How does that sound? That's exactly right. So what did I do in the image? I replaced these two disks by that tube, but those images were all sitting inside of a B4. B4 has no contribution to homology. So that doesn't make a difference. And then finally, to sort of finish the construction for the other Ds, what will you do? Well, for any other D, you'll just have as many two spheres, but they'll intersect in D choose 2 spots. So perturb to make sure they all intersect in, pairwise intersect transversely. You can do that. There's enough room to do this. So for larger D, the same argument will have, we get D 2 spheres. And at each transverse point of intersection, you take out the two disks and you glue in tubes. So you get D choose 2 tubes. And you have to convince yourself that the genus of that surface is exactly that. And let me not do that since I'm running over time as expected. Does that make sense? So maybe it's a good exercise to think about the D equal to 3 case. So you have 3 spheres. So in the D equal to 3 case, you'd have 3 spheres, and you'd get tubes like this. Notice that 2 of these tubes did not add genus. They just connected everything. And the last one is the one that added genus. Similarly here, we just got S2. So in the D equal to 1 case, you got an S2. In the D equal to, goodness, I can't do that in my head. D equal to 2 case, you got an S2. D equal to 3 case, you'll get a torus by this construction. Okay. It's 11:30. Let's take a 5-minute break. Let's start back at 11:35. Feel free to stretch, walk around, go to the bathroom, send me some feedback, whatever you like. I'll erase the boards. That's a good question. Part of it is that we don't have good invariance. This is part of it. It's because this is a indefinite intersection form, we don't have good invariance for this. That's part of the motivation. You should read, there's this paper of Marangon, Piccirillo, and Manolescu. Marangon, Manolescu, Marangon, Piccirillo, where they talk about this question. And they have this idea of whether you can use these slicing questions to detect exotic spin structures. So that was the motivation there. I meant to mention this, but I didn't. specific reason. I think it was like, if you look at your toolbox of slicing obstructions, it turns out that like, yeah, I think this was, you should read that paper. But I think essentially it comes more from the invariant side rather than, I mean, you know, like we already know that K3 has exotic smooth structures. So in that sense, that shouldn't be a motivation. But it's really sort of, you know, we should try to do it in CP2 where we don't have exotic smooth structures. That would be more useful in that sense. Sorry, not a good answer, I'm afraid. Do you have a question?
The same as smooth James function for the other. So the question is, can we, like, is there an example where we have distinguished a pair of exotic four manifolds by using the smooth James function, or not really?
I think they exist. I'm trying to think of, it's putting it the wrong way. Okay, I believe they exist, and I'm failing to come up with right now. The question, like slicing of knots and links, can be used to distinguish between smooth structures. So there are examples where you have an exotic pair of four manifolds, and you've picked a knot, and that knot is null homologously sliced in one of them, but not the other. So in that sense, that might count as an example. And in the absolute case, I believe there's an example, but I'm forgetting. So if you ask me in a more relaxed time, I might be able to remember. But I believe that that's done. I just don't know. Don't remember.
Just like a mini question, like for this is not like the easy implication part, the fact that we can realize class by d minus factor minus 2 over 2. Wouldn't you also prove it like some algebraic geometry?
Yes, absolutely. So you can do that. And in fact, what one can do is you show that the complex, that thing that I erased is the minimum genus of a complex surface representing that class. And what Kronheimer and Mruvka showed more generally is that like those will always be genus minimizing. So you're absolutely right that there can be other constructions of that.
Is that you prefer to give more topological approach?
It's very generous of you. Let me say that I don't understand algebraic geometry, and therefore for me it's like I couldn't possibly give you an algebraic geometry approach. So, sorry you're out of time. You're welcome. Yes, this is what often happens. I know, but at least today there won't be an hour of questions afterwards because there will be lunch. That makes sense, right?
So it realizes the...
Let me, I can just start, if that's okay. Great. Thanks for coming back again. I hope that was a good break. And maybe you feel a little bit more refreshed. I'll try not to go over time to make up for it. But anyway, thank you. There were a couple of questions during the break that I wanted to address. The first question was about specifying the homology class of surfaces inside of four manifolds for knots. And I just remembered that I totally forgot to mention something very important, which is the case of knots in the boundary of punctured four manifolds that bound null homologous disks is something that people have studied a lot. So that's not quite the question you asked, but it's in that vicinity. And so this is something that, so in terms of slicing knots in general four manifolds, a nice reference for that sort of question is a paper by Manolescu, Marangon, and Piccirillo. So I invite you to look at this paper. In particular, you'll find some motivation about why they care about slicing knots in the K3 surface. And in particular, one of the things that they showed in this paper is that the set of null homologous slice knots, meaning knots that bound disks that are null homologous, can be used to distinguish between exotic four manifolds. So they show that you can have a pair of four manifolds that are homeomorphic but not diffeomorphic. And then if you consider there is a knot that is null homologous slice in one of these, but not in the other one. And so this was not like a new example. So these were four manifolds that we already knew to be exotic, knew to be homeomorphic but not diffeomorphic. But they showed that the sort of slicing knots in four manifolds approach can be used to attack that problem. So I think a lot of the questions that I heard in the 5 minutes were related to this. So I wanted to mention that. All right, so I promised you some topological obstructions. And yesterday I promised to show you that not all knots are slice. So I thought that I would give you a slicing obstruction as a sort of topological obstruction. Okay. There are obstructions to the absolute setting as well, but they are harder to describe, and I would rather not. So the thing that I'm about to describe is something pretty computable and more or less friendly. So I thought we'd do that. So okay. Right? Suppose you have a knot. You always have a compact-oriented surface with boundary that knot. This is called the Seifert surface. And let me draw you a picture of these things. So here's my favorite knot. No. Here's some knot. This is a left-handed trefoil. Let's put an arrow on it because knots are oriented. It's the boundary of a surface. You can see it, right? It's this flat thing that I've drawn. It's this. There's this square, and then there are two bands. They're twisted. There's a Seifert form, which will go from H1 of the sigma to the integers, which will take x comma y and then map it to the linking number. The linking numbers of x and y are lying on the surface, and they potentially intersect, so that's not very good. So what you do is you take the second one, and you float it just above the surface. So let me tell you what I mean by this. So here, let's say this is A, A, and this is B, you believe that these two circles generate the H1 of this surface as a punctured torus. This surface, sigma, well, my knot was oriented, so my surface is oriented, so it has an up direction and a down direction. In this case, the up direction, following the right-hand rule, is towards you. So if I were to compute the linking number between A and B plus, well, B plus means take the curve B and float it above the ciphered surface, so like off the blackboard in your direction. Okay. Then linking number is computed as always. I will not talk about that. In this case, for this surface that I've drawn over here, assuming I've done it correctly, the ciphered form will be represented by this ciphered matrix that will be given by the linking numbers of these curves. And the main thing you notice is that if you pull B plus, if you pull B off in front of the blackboard, you get this linking over here, which is a +1. So there's a +1 here. There are these twists, which means you get ones in the diagonal. But if you were computing the linking number of A plus and B, if you float A off the blackboard, it's just fully above B, so you get a 0. And then the signature, so this is a ciphered matrix. Then the signature of the knot K which is denoted sigma k, is by definition, you take such a ciphered matrix, you add its transpose to make it symmetric, you compute its signature, and that's the signature of the knot. Okay? By the way, Powell mentioned the Alexander polynomial. The Alexander polynomial is by definition the determinant of V minus TV transpose, where T is the variable that you'll see in the Alexander polynomial. I will not use that, but just it came up, so it's a very computable thing. The result I wanted to prove to you is that not all knots are slice. And in particular, here's this theorem. Let me attribute it to Murasugi. This says that if K is topologically sliced, we're back to thinking about slicing in B4. So I'm just thinking of B4. Okay, so if my knot K bounded a locally flat embedded disk in B4, then the signature would be 0. If you compute the signature of this knot, so the signature of this V plus V transpose, you'll notice that for this K, let's call this J, you'll notice that signature of J is equal to 2, which is not 0, therefore this is not slice. Okay. More generally, signature gives a lower bound on the topological 4 genus of knots. I won't prove this part. So you can see this knot has ciphered genus 1, namely it bounds a genus 1 surface in S3. So it's sort of obvious from this fact that it was going to be less than or equal to 1, the 4 genus, topological 4 genus. And that result tells you that it's exactly 1. And then you can also take connected sums of this if you wanted to get the signature to get arbitrarily large, to get knots of arbitrarily large topological 4 genus. 2, here, right? Yes, sorry, my bad. Thank you. Okay. This is an extremely computable invariant. That's part of what I wanted you to see from here. That topological invariants, in some reasonable sense, they are algebraic. So these are like the simplest, this is the simplest algebraic invariant that I know of for knots. There are more and more sophisticated invariants, slicing obstructions, etc. But they're all very algebraic in a certain reasonable sense. And that's part of what makes it so purely topological. Whereas the smooth invariants that you'll hear about in the other mini courses, they'll have a lot of theory behind it that will make it sort of super smooth. There's nothing very smooth that's going on here. Question? Ah, yes, okay, thank you. Nah, that makes much more sense, thank you. I didn't get a 5-minute break. That's anyway. Thank you, that's very important. Okay. So I want to sketch for you this proof. Let me skip details because we don't have time for them. So just of the first bit, you start with your, what am I going to say? So you start with your, you start with your knot. This is a schematic picture now. And it's the boundary of some Seifert surface. Let's say sigma inside of S3. And here's B4. And you're assuming that there's a slice disk. The slice disk is supposed to like leak into this fourth dimension. Right? The first step of the proof is there exists a 3-manifold, M3, sitting inside of B4 with boundary, which is bicoloured, and with boundary equal to the union of sigma with like a little push-off of this disk delta. So you should think about that 3-manifold is like here somewhere. There. So there's something that fits in here. Okay. Very quickly, let me say that the point is that the key point is that H upper 1 of B4 minus this delta is isomorphic to the integers. So in particular, this corresponds to some map. Delta plus is, I just wanted to push it off a little bit. Let me ignore it. In a sketch, it doesn't matter. I think you asked it. In the sketch, it does not matter. But if you were to follow, if you were to go through this thing that I'm about to write in orange, you'll see why it matters. This complement of delta has H upper 1 Z, and that means that there's a map from here to KZ1, which is S1. And this M3 is going to come exactly very similarly to what we did in our first proof. We're going to make this map transverse to some point and pull back said point, and that will give me some 3-manifold. You have to be careful about this boundary condition, and so you have to do that very precisely. And Gregor, the point was that I'm trying to construct that thing in this complement of a tubular neighborhood, so I couldn't really attach the actual disk because it's like in the thing I removed. So I should float the disk off into the boundary and do it there. But this is not important for anyone who's only seeing a sketch. There's a three-manifold here. Okay. Step 2 is you use something called half-lives, half-dies. This says that if you have a compact, so the statement of half-lives, half-dies, which, by the way, is an extremely helpful fact about three manifolds, homological fact about three manifolds, it says that if you have a compact orientable three manifold with boundary of M genus G surface, then, and I is the inclusion, then if you look at the kernel of this I star map on H1 with rational coefficients, this has rank G. Okay. So the intuition for that result is the following. So in the most obvious compact orientable three-manifold with boundary of genus G surface, namely the handle body, let's draw the handle body of genus 2. So I'm claiming, the surface, H1, so I can consider this handle body, which is M3, and the boundary is the genus 2 surface. H1 of the boundary is obviously Z to the 2G. And I'm saying half of those will live and half of them will die. Okay? So in particular, if I had this solid handle body with its boundary, the genus 2 surface, here are the generators of H1 of the surface. And you'll notice that these two, the ones in red, will die in H1 of M3. And then these guys in green, these will live. Okay? I will not prove this. It's like Poincare duality, Hom duality, diagram chase. Not too difficult. Okay? But essentially it's saying that the thing you're used to from handle bodies actually holds for totally general three manifolds as well. Half of these surface generators will live and half of them will die. And I want to apply it to the three manifold that I have there in my picture. And so what does it mean? What do I have? Well, I know that this means that there exists a basis for H1 of my sigma union delta, such that the top half, x1 through xg, bound rational two chains in my three manifold, where I can also assume that these x1s through xj, g, they lie inside of my ciphered surface sigma, because the disk is a disk. So if I have some curves lying in that surface, I can just choose a representative that just lies in the ciphered surface part of it. Okay? Have I lost everyone? Are you still with me? Okay. Someone very confused? Is it me? let's just quickly finish this. So what I know is that there exists Ni such that Ni xi is equal to 0 inside of H1 of M with Z coefficients. In other words, what that means is that Ni xi is equal to the boundary of such a two-chain. I'm going to write some things here. But before I do that, let me just tell you what the end result is, in case I'm sensing that I'm losing people. Maybe I'm wrong. The end result of this will be that my Seifert matrix V will be of the form, so where this is like 2G by 2G, where G is the genus of the Seifert surface, and then these are G by G blocks. Yeah? So I want to convince you that the Seifert matrix looks like this. It's built up of 4 G by G blocks like this, and then there's one block which is just fully 0. Because then I can use my algebra fact that in this case, you can try to compute the signature of a matrix like this once you symmetrize, and it will be 0. And that will be the argument. Okay? So right now, I'm trying to convince you that there's a block of zeros like that in the Seifert matrix. Okay? So in order to do that, I need to tell you about linking numbers. And in fact, these xi's are the ones that are going to correspond to that 0 block. So I'm going to have like x1 through xg. So I just need to tell you that those linking numbers of all of those xi's are 0 with one another. And once I do that, I'll be done. And so that's exactly what we were doing over there. So M is bicolored. So that means that I could take this xi, which lives in M, and push it into the bicolor. Okay. Bicolor means that M cross interval lives inside of that before. So my whole three-manifold has a cross I direction. So I can float things off and remain disjoint. Okay? So in particular, this means that I can take xi plus is equal to the boundary of ni xi plus. It's the boundary of this thing, where this is a push-off in the bicolor direction. So that now, when I compute the linking number of ni xi with ni xi plus, this kind of by definition of linking number is equal to the intersections, the sign count of intersections between xi and xj plus. But because the pluses are just off in the bicolor, they don't intersect anything in the M. So this is just always 0. But what is this? This is ni nj linking number xi xj plus. And if that product is 0, then like that is 0, because these are non-zero. And so this implies that linking number of xi xj plus for is equal to 0 for all ij. And that implies that I have this block of zeros in my Seifert matrix, and that implies my algebra fact, and that completes the proof. Yeah, the reason for that is because of this plus over here. So I really wanted the fact that the three manifold I built over here has a cross-interval direction that's compatible with the bicolor on my Seifert surface. And so you could think about this as like, this is the boundary of something in M cross 0, and then this xi plus, this will live in M cross 1. And so there's no intersection even when I and j are the same, because that's in M cross 0 and that's in M cross 1. And those are totally different. Okay. Sorry? Oh, yes, sorry, my bad. Thank you. Thank you. Hey, the details of this proof do not matter. Let me take a minute to sort of point out something about the flavor of the argument. The signature is an extremely computable invariant. Like, once you give me a knot, writing down a Seifert matrix, computing the signature is not that hard. And it can give you some control over this kind of abstract fact about genus of surfaces inside of B4. Techniques are very topological. They're very direct. It's kind of like, it did require some amount of steps, but that's because I was trying to do it in 15 minutes. It's not that complicated. We can all do this. It's like, you could have all done this in first year of your master's or something like this with sufficient sort of some amount of background information. So I just want you to know that these are like completely computable, accessible, topological obstructions that, of course, also obstruct smooth things as well. So if your knot is not topologically sliced, it will also not be smoothly sliced. I did not get to talk about topological constructions. I don't completely know whether I'll do it tomorrow or not. So my plan tomorrow was to talk about uniqueness problems, and I could just do that. But if you would like me to talk about topological constructions, I can also do that. So maybe between today and tomorrow, let me know if you have a preference or use the online form or something like that. We still have day 4 as a buffer, so we can sort of explore what happens there. All right, thank you.